Hello and welcome to this video on evaluating expressions of the form a to the 1 over n power, or a to the 1/nth power, base a, and exponent 1 divided by n. So in this video I'm going to talk about fraction exponents, or rational exponents of this form 1 over n, and how they're really the same thing as radicals. And I've put up previous videos on radicals, roots, square roots, cube roots, fourth roots, etc. So I'll discuss how an expression of this form is related to a radical, and then go over several examples. Alright, so my first page here, I'm going to just discuss rational exponents. Rational, or a fraction exponents. And for this particular video, I'm not going to do every single fraction. We'll get to that in a future video. I'm just going to look at exponents of the form 1 divided by some integer n. All right, well, some positive integer n. All right. So in order to talk about rational exponents, we need to remember one little property of exponents, and that's the product property, right? Or I guess you could call it the power to a power property. Of exponents. And that was the following. If I have a number, say the number represented by the letter a, I raise this number to an exponent, say the nth power. So remember, this is called the base, this is called the exponent. Again, I'm not going to write all that down. That should be hopefully familiar to you by this point. And if I take this expression here, a to the nth power, and raise it to another power, say to the nth power, what that's equivalent to is you can keep the original base, so base a, and the new exponent is going to be simply the product of these two here, right? So a to the nth, and then that to the nth is equivalent to a to the m times n, or a to the mn power. Alright, so let's keep this in mind, this property of exponents, power to a power property. And what we're going to do here is think of roots, and what we're going to see how these 1 over n powers here are related to roots. So some examples down here. Right, so here I'm going to do some examples of when we had radicals or roots. So hopefully you recall that when you take a square root, right, when I take the square root of 2, let's say, and raise it to the second power. Remember, this just meant the square root of 2 times the square root of 2, right? Or remember, the square root of a number was when you saw this symbol, was the non-negative number that when raised to the second power, would give you the radicand. So the square root of 2 to the second power, square root and square basically like undo one another. You're left with the radicand of 2. Well, let's think about this another way. And you're going to see that in a second here that radicals are going to be like these, are going to mean the same thing as these fraction exponents. Instead of thinking about this as the square root of 2, I'm going to think of this as 2 to some exponent. Right, so 2 to the, I don't know, I'll use x, some unknown exponent. And I want to say, 2 to what power, when squared, would give me 2, just like over here. Over here the square root of 2 to the second power gives me 2. But here I am saying 2 to what power squared also gives me 2. And this is where that power to a power property comes in. This left side, I have 2 to the unknown power x, and then that again is being raised to the second power. This is equivalent to 2 to the x times 2 power, or 2 times x, or 2 to the 2x power. And in order for that to be equal to 2, the powers need to be the same. And again, we'll get into videos later on exponential functions and the fact that they're 1 to 1 and all that, what all that means. But for right now, just know that if 2 to a power is equivalent to 2 to some other power, right? If two expressions are equivalent and have the same base, they must also have the same exponent. All right, so this implies that the 2x, right, the exponent on this side must be equal to the 1, right, the first power on the other side. And then dividing both sides by 2, we see that that power I said earlier, the x power, must be 1/2. So this must be 2 to the 1/2 power. X is 1/2. So 2 to the half squared is 2. But we saw earlier with roots, with radicals, that the square root of 2 squared is also 2. So this leads me to the following statement, putting both of these together, that the square root of 2 is equivalent, means the same thing as 2 to the 1/2 power, 2 base 2 exponent 1/2. All right. And let me take a look at another example. And what you're going to see is that these radicals, square root of some radicand is equivalent to taking that radicand to the half power. You're going to see that the radicals are equivalent to raising the radicand to some fraction power. All right, so another example. This time I'll work with a cube root. So in radicals, if I had the cube root of 3, say, and raise the, let's make that 5, why not, so I don't see 3's all over the place. All right, so how about the cube root of 5? If I took the cube root of 5 and then raised that to the third power, right, to undo the cube root, you'd be left with just the number 5. All right. Or, and then again, I'm going to do the same thing I did over here with the 2 to the x and all that. Instead of thinking of this as the cube root of 5 being raised to the third power, let's think of this as 5 raised to some power, right? 5 to what power, when cubed, will also give me 5. Right. And let's see. Over here I can apply that power to a power rule, right here. And 5 to the x power, 5 to some power, and then that raised to the third would be 5 to the x times 3 power, or 3 times x, 3x, right? Equals, and then the other side's 5 to the 5 to the first, right? Just 5. And in order for these to be equal, right, in order for two numbers with the same base to be equal, they have to have the same exponent. So this implies that the 3x, the exponent on the left, must be equal to the 1 on the right. And then dividing both sides by 3 here, I see that the value of that power, that x, must be a third, right, 1/3. So putting these two statements together, looking at both of these, I'm seeing that the cube root of 5 to the third is 5, but also 5 to the 1/3 power to the third is 5. So looking at both of those, we see that the cube root of 5 is the same thing, right? This base here, the cube root of 5, is exactly the same as this base here, which is 5 to the 1/3 power. All right, so look at this. Square root of some radicand is equivalent to that radicand raised to the 1/2 power. The cube root of some radicand 5 is equal to that radicand 5 to the 1/3 power, 1 over 3. So what you're going to see in general, then, and here I'm going to write the relationship between these radicals and these fraction powers 1 over n. So in general, the nth root, if I'm looking at a radical, the principal nth root of some number a, I'll use a lowercase a there like earlier, can be written in an equivalent way with an exponent, with a fraction exponent. So the radicand, as you saw, the radicand becomes the base. So a is the base now. And then whatever the index on the radical was, right here this had an index of 3, that's the denominator on the exponent, right? Or you could say the reciprocal of the index is the exponent over here. All right, so this is a to the, and then the index on the radical is n. The reciprocal of n is 1 over n. And I'm also going to make the statement here that because if n were even, remember you can't take even roots of negative numbers. That'll be not real. But you can take odd roots of anything. Just to cover everything, I'm just going to say that a is non-negative off to the side. All right, so the value of a here is non-negative. That way it'll always be a true statement for no matter what value n is. All right. So I'm going to put this in a little box for you. Please remember this. Okay, cut it off maybe here, but remember this part. How you can translate, how you can go back and forth between having a radical with an index of n and an exponential statement with a power of 1 over n. And I'll write out what happens again down here, below this. So the radicand on the left side becomes the base over on this right side, right, when I write it as an exponent. So the radicand of a becomes the base on the power. And then the index of the radical, which is n, right, what root you're taking, you do the reciprocal for the exponent. Over here, right? So index n, power, exponent, 1 over n. You saw that here. Index 3, power, exponent, 1 over 3. This one, the square root of 2 equals 2 to the half. Remember when there's no index on the radical symbol, it's an index of 2, square root, right? So index 2, and you see the exponent is the reciprocal, 1 over 2 on the other side. All right, great. Okay, and then all the same rules apply, right? And I've talked about radicals before in previous videos, evaluating nth roots and evaluating radicals of the form, the nth root of a to the nth power. You have to really pay attention to whether or not the index is even or odd, right? So remember, if the index is even, this symbol means you're asked for the non-negative nth root, right? It has to be non-negative. Additionally, remember, if this is even 2, 4, 6, 8, the radicand also has to be non-negative, right? An even root of a negative number is not real, right? Not a real number. And then when this was odd, right, 3, 5, 7, 9, etc., it didn't matter, right? You can take the odd root of a positive radicand, you can take the odd root of a negative radicand, or 0, and the result will be respectively positive, negative, or 0. Right? So odd roots were a lot simpler. Okay, so now that I've got that down, right, I've established the relationship between radicals and these expressions with exponents, these fraction exponents, 1 over n. Let me take a look at it. I've got several examples where we're going back and forth between these. So my first set of examples starts off as an exponential statement, and we have to change it to a radical statement, all right, with the radical symbol. And the other examples I'm showing you today are, I have a radical statement and I'm asked to rewrite as an exponential statement. You should be able to go back and forth pretty easily. All right, so my first of these, and I'll keep the formula up here, the relationship up here. And for each of these first ones, I'm going to be doing the following instructions. Write each of the following expressions as a radical, all right, so involving the radical symbol. And of course, let's simplify, if we can, right? If it's actually a real number. All right, so look at this, right? Here I have 25 to the 1/2 power. So remember, 25, the base 25 becomes the radicand, right? So this is equal to, I'm going to make the radical symbol, and then the base over here, again, the base on the power, the exponent is 25, the base is 25, exponent is 1/2, base is 25. The base becomes the radicand, right? The expression underneath the radical symbol. And then the index is just the denominator, right? The index of the radical is the denominator of this 1 over n power, right? So 1 over 2 means I'm taking a square root, right? This is going to be a square root over here. That's what it means to raise to the 1/2 power. This means the same thing as taking the square root. All right, and can we simplify? Now remember, when you see this symbol, I've said this a bunch of times in previous videos, when you see this radical symbol and there's an even root, an even index, you're asked for the the non-negative number whose square is the radicand, right? So what's the non-negative number whose square is 25? And that would be positive 5, right? So 25 to the 1/2 power is positive 5. All right, and if you want to maybe believe it a little more, right? These are exponential expressions. You can very easily enter these in a calculator if you want to, just to check yourself. So I've got a TI-84 here. A lot of calculators have power features, raising to powers. But you can just simply go 25 raised to a little caret button, and then the 1/2 power, right? Make sure that's all in the exponent. And you'll see this ends up giving us positive 5, which it does here, see? Okay. All right. My next example, another one just like this, where I have an exponential statement with one of these fraction powers, and I'm asked to write as a radical, and then simplify. All right, so here I have, let me get rid of this bottom one. So negative 27 to the 1/3 power. All right, notice the parentheses. All right, the parentheses have a huge meaning here. This is totally different from the following. If I put negative 27, minus 27, and then on the 27 I put to the 1/3 power, these are totally different. Again, because of the placement of parentheses. In the expression I have over here, the exponent is 1/3. The base on that exponent is everything in the parentheses here. The base is negative 27, not just 27. Whereas over here, when you see a minus sign, right? Remember, anytime you see a minus sign or a negative sign, it's really just like having a factor of -1. So what I have over here is equivalent to -1 times, right? Because there's no plus or minus after the minus sign. -1 times, and then 27 to the 1/3 power. So on the left side of my page, the exponent of 1/3, the base is, all in parentheses. It's this entire thing, negative 27. On the right side of the page, when there aren't any parentheses, this negative sign implies that I have a factor of -1, and under the exponent of 1/3, the base is only the number 27, not negative 27. All right, so please pay attention to whether or not I have a set of parentheses placed or not. All right, so back to my original example, I have this, in parentheses, negative 27 to the 1/3 power. I'm going to write this as, as a radical. So I'm going to this is equal to, I'll put the radical symbol. Remember, the base is the radicand, right? So negative 27 is going to go underneath the radical symbol like this. And remember the denominator of the power, right? The denominator of this power, 1/3, the denominator is the index. All right, that's going to go right here. All right, now this is an index of 3, so that's a cube root, right? I put the 3 there where the index should go. So this negative 27 to the 1/3 power is the same thing, means exactly the same thing as the cube root of negative 27. And hopefully we know how to simplify this, right? Negative 27 is a perfect cube. You think of, this is an odd root, so it doesn't matter that this is a negative radicand, right? You can take the odd roots of anything. And all you're thinking of here is what's a number that you can raise to the 3rd power to get negative 27, and that would be -3. All right, -3 to the 3rd power is negative 27. And great, and again, if you want to double check this, let me show you again now. All right. I put in parentheses, negative 27, close the parentheses, raised to the 1/3 power, and you're going to see -3 in my calculator. Right? Okay. Now I know that this is also -3 over here. Let's see, but it would look a little different because again, this minus sign is not in parentheses with the 27, so the minus isn't part of the base. The base on the 1/3 is only 27. So this is -1 times, and then this is what I would write as a radical. All right, this 27 to the 1/3. So again, I'm writing it as a radical. 27 is the base, so that would be the radicand. So I pop a 27 in here. And this is 1/3, 1/3, right? 3 in the denominator is the index of the radical, so this is the cube root of 27. So what I have here is -1 times, or just minus if you want to leave it as minus, but -1 times, and then what's the cube root of positive 27? That'd be +3. And yeah, -1 times 3 is -3, cool. But still, just even though they have the same value, right? Both of these, this expression where my finger's pointing, this expression where the marker's pointing, yes, both of these have a value of -3, but they are different. They have a different meaning, right? They have the same value, but they have, the exponent of 1/3 has a different base in each of them. So just pay attention to parentheses. And really that's also what my next 2 examples are showing as well, right? To pay attention, do I have a set of parentheses or not? So another one of these where I have a fraction power, right? Now this is just like the one with the, there's no parentheses around this. So this minus sign here is just like having a factor of -1. Right? It's like having -1 times, and then this 64 to the half. All right. So the base on that exponent of a half is just the 64, not the -64. It is not in parentheses. Okay. So now I'm going to write this as a radical. Again, this -1 out here is just on the outside. It's still just -1 times, right? That is not going to be in the radical. The only stuff involved in the radical are the base and fractional power. So 64 to the 1/2, and I'm going to write my radical symbol. The base is 64. Remember, the base is the radicand, so it goes underneath. So I have 64 underneath the square root symbol, or the radical symbol. And then yes, it is a square root, right? This is 1/2. The denominator of this power is 2. So the index of the radical is 2. Now again, usually 2 is not written, but I'm going to leave it alone. This is a second root, or a square root. And we can simplify this, right? Again, you got the minus sign out front. That's not going away. That's the factor of -1 times. And then what we're seeing here is what's the non-negative square root, right? Remember, when you see this radical symbol and there's an even index, you're asked for the non-negative root. Because I know -8 squared is also 64, right? -8 times -8, but we're looking for the positive one, the non-negative one. So the square root of 64, or the principal square root of 64, is positive 8. And what is -1 times 8? Totally simplified is -8. All right, so the value of that expression is -8. Again, let me punch that in for you. And notice I'm gonna have no parentheses. Just have a minus sign, or a negative sign, and then 64 raised to the 1/2 power. Again, notice just the difference between these. No parentheses here, and you're going to see this ends up being, say, -8. Right. Wonderful. Okay. Now look at the big difference between this example and the next one. And it's the same as I showed before. Put this side by side. Notice the parentheses again. All right. So this time, on that exponent of 1/2, this whole thing is the base on that power of 1/2. The base this time is not just 64, but the whole thing in parentheses, the -64. And I can write this base to a power as a radical. Right? Only the base to the power can be written as a radical. So as a radical, I'm going to write the radical symbol. All right, the base is -64. The base becomes the radicand. Right? I write the base inside the radical symbol, so -64 in here. And the index is 2 again, right? This is the half power, 1/2. The index is 2. So this is a square root. And, there is a big problem here this time. Right? I'm taking an even root. Right? This is an even root, a square root. But the radicand is negative. That is a problem. All right? Remember, like this is not a real number. I've done this in other videos. There's no real number that when you square it gives you a negative number back, right? Any positive number squared will be positive. Any negative number squared, right? Negative times negative will also be positive. So this is not happening on the real number line. There's no rational number, no irrational number that makes this -64 when you square. So I can't really simplify this. All I would really have to say here at the moment is that this is not a real number. Okay, and that's it. Nothing to do there. All right, can't simplify it. Now, in a future video, we will talk about some non-real numbers and what the set of imaginary numbers, and be able to talk about how else to express like the square root of -64 here. But for right now, with the material I have, with the information I have, I'm going to simply say this is not a real number. Okay. All right, and then my last example of this, so far all my examples where I had a base to a power somewhere and wrote it as a radical have had just numbers involved. That's not always the case though. You might have variables too, right? So this last example, a pretty quick one, pretty simple one. I just have, there's a B for base, right? This is the letter B, and this is B to the 1/2 again. So as a radical, I got my base to a power. I write the radical symbol. The base is this letter B, so that becomes the radicand. And the index is again 2, the denominator of this 1/2 power here, right? So this is the square root of B. And then maybe off to the side, because I have an even root, I might mark off the domain. All right, what am I allowed to plug in for B? All right, B can't be negative here if I want to have a real output. All right, so I'll maybe mention off to the side that the value of B has to be greater than or equal to 0. Right? B can't be negative, or you'll have exactly what happened in the last example where I have like the square root of a negative, and that's not real. So I'll just put that B has to be greater than or equal to 0 in order for this thing to be real. All right, but there you go. All right, B to the half is the square root of B, the non-negative square root of B. All right, great. All right, so those examples I had some base to a fraction power to the 1 over n, like this side, and had to write it as a radical. Now the next several examples I'm going to be going the other way. I'm going to see a radical and be asked to write it, an expression with a radical in it, and be asked to write it as an expression with this base to a fraction power. All right, so my next example, and the last few of them, I have the following instructions. Rewrite each of the following radicals with a rational or a fraction exponent. Okay, so look at here. I've got the 5th root of 8b as a variable again. So the radicand is this 8b, right? And that'll become the base of the exponential statement I write, right? So this 5th root of 8b is 8b as the base, right? And I want that whole thing to be the base. Okay, so I'm going to put it in parentheses. Just like with the negative sign before, if you don't put it in parentheses, only the b will be the base, and I'll show you that in a second. So the radicand of the radical becomes the base of the exponential statement, and the index of this radical is 5. All right, the index is 5. This is a 5th root. So the exponent that we're raising this radicand to when I write it as an exponential statement would be the reciprocal, right? The reciprocal for the exponent. The reciprocal of the index, 1/5. All right, so this quantity, this 8b in parentheses to the 1/5 power, means exactly the same thing as the 5th root of 8b. Right? So this is all great here. Right? Now be careful. Right? Now, some people would just write this. Right? This is not 8b and then to the 1/5. Remember, what parentheses mean something. All right, I'll put them not this. All right, because parentheses mean something. In this expression, the base on that power of 1/5, the base is that entirety of 8b. But over in this expression, the 8 is not raised to the 1/5. It's not under the 1/5. I mean, it is under the 1/5, but it's not in parentheses under the 1/5. The only part of this expression that's actually the base of the 1/5 under the 1/5 is the b, and that's it. Not the 8. Just the b. All right, so totally different. These are totally different. So you would not write that for my 5th root of 8b. For the 5th root of 8b, you got the 8b in parentheses to the 1/5 power. All right, and just a couple more of these where I have a radical and very simply just going to be writing as an exponential statement. All right, so again here I have a radical. This is the 8th root, right? Index 8 of, and this time the radicand is this whole expression underneath the radical symbol, right? The radicand is this m times n to the 5th power divided by 3. So this becomes the base Right, the radicand of the radical becomes the base of the exponential, the equivalent exponential statement. And again, I don't want to write just this and leave it like that and then put the 1/8 power. If I want this whole thing to be the base on the exponent, I'm going to put it in parentheses. All right, so now it's all the base on this power I'm going to put. And the index on this radical is 8. Remember, for the index, you take the reciprocal for the exponent on the exponential statement. So the index of the radical is 8, meaning the exponent of the equivalent exponential statement will be 1/8, 1/8. And that's it. Put in a box here. This expression here, this expression means exactly the same thing as this expression. All right, one is a radical though, and one has an exponent. All right, one last one. Now pay attention again here. You know, this 4, I have 4 times the cube root of y. The 4 is not part of the radical, right? It's not the part of the radicand. The only thing that's the radicand here, the expression underneath the radical symbol, is that variable y, and that's it. And the index is 3 on this radical. So this 4 out here is going to stay outside. So this is equal to 4 times, if you want to write the little dot for times, that's fine. That's going to be 4 times, and then this is the expression I'm going to rewrite with a fraction exponent. The radicand is y, so that'll be the base, right? And since it's only one factor, just y, you don't need to put it in parentheses. There's only one factor, not like the previous examples where there were multiple factors, so I put it all in parentheses. So base is y, and then the exponent would be 1/3, right? The index is 3, so the exponent on just the y, right, on just the radicand, is 1/3, not on the 4. Right? The 4 is to the first power, if you really want to put a power there. So this 4 times the cube root of y is equivalent to 4 times y to the 1/3 power. And no parentheses around the 4y. And remember, this is not the same thing as the following, where I put, if I did this, right, that would be wrong. And you can double check by replacing y with some values, or just saying, hey, this thing over here is actually the cube root of 4y, where the 4 is on the inside, right? The 4 is actually part of the radicand, part of the base. Here the 4 is not part of the base, 4 is on the outside. So like this would be incorrect, all this, right? I want 4 on the outside times, and then the cube root of y is equivalent to y to the 1/3. All right, wonderful. All right, so please get that relationship down. You're going to see it a lot. The nth root of a is equivalent to a to the 1/nth power, and vice versa. Okay, and as I like to say at the end of these, try the best you can to learn the material on your own before you go looking for help. I find that people who take the time and the effort to learn things on their own tend to remember them for longer and better. So read the material, of course, read the author's examples, perhaps even try to work out the solutions to some of the author's examples before you look at how the author did it, and then compare your work with the author's and see if you can learn from some mistakes there. Obviously, do loads of exercises, practice problems, look up solutions to them whenever they're made available, and don't just give up on a problem after one attempt. There are very often several ways to approach a math problem that'll work. So if after several attempts, several approaches at a problem, you're still not getting it, still not making sense to you, perhaps you should read through the material again, maybe even a third time, more slowly, more deliberately, take notes. Because if you've been working on some problems, there's a good chance that you have a better idea as to what the author wants from you, what the author expects from you. So then you'll probably have a better idea also as to what to look out for when reading the material. So that second or third read through, might shine some light on some things that you didn't see the first time. But if after that, if after several read throughs of the material and several approaches at problems, you're still not getting it, still not working out for you, well then it is not a sign of weakness whatsoever to go out looking for help. That is what other people are there for. So ask a teacher, a tutor, a friend, someone in your class who you know knows the material well and is willing to help. Look for supplemental materials online. There's tons of it out there. Look for videos on the subject. There's tons of those too. Videos like this one, or plenty of other ones out there that are better than mine. I assure you, you can find them very easily. But just keep at it, is all I'm saying. Stay persistent. Keep practicing. Don't give up. And I think the hardest part is to have a positive attitude about the subject. Try to have a positive attitude. If you go into something thinking you're going to hate it and that it's boring and you've always hated it, well, you're probably going to continue to think that, and it's going to make the learning experience that much worse. So if you go into something with an open mind, thinking, I'm going to read this today, I'm going to do these exercises, I'm going to learn something, I'm going to enjoy learning it, I'm going to take something away from this for my class, for my life, whatever, and have a positive attitude about it, you'd be amazed at the change, you'd be amazed at the difference that a change of attitude can make. So please stay persistent, keep practicing, stay positive, don't give up, and I just know you'll get it eventually. And thank you very much for watching.